All right, good day, everyone. Thank you very much for joining today's webinar presentation on grasping some publicly available aerosol data with Dr. Jeffrey Reed from the Naval Research Lab. Normally, we have a little intro video that we play, but for some reason, the sound is not coming through correctly today. So I'll just kick it off with a little bit of an introduction of what HDI is, and then explain the webinar and some admin things, and then turn it over to Dr. Reed. So HDIAC is the Homeland Defense and Security Information Analysis Center, and we are a government-funded research organization with which falls under the Undersecretary of Defense for Research and Engineering. And we provide a number of services to government-funded researchers, including contractors, to help unlock and uncover government-produced research, as well as research from other entities also. And we have 8 different technical focus areas, among them being seaborne defense, medical, homeland defense and security, and critical infrastructure protection, which is what brings this webinar to us and makes it important for the community. Before I turn it over to Dr. Reed, I just want to give you a couple of administrative announcements. First off, all participants are muted. You can feel free to use the chat function, which should be in the bottom right-hand corner of your screen. To the right of that chat function should be a 3-dot ellipses menu, which has a Q&A function in there. If you want to ask a question at the end of this presentation to Dr. Reed, please try to use that Q&A function. It's just the easiest way for me to make sure I capture all the questions. I'll try to capture things in the chat, but if it's in the Q&A, then it's almost guaranteed I can get to it. The slide presentation is up on the HDI website. Once I'm done talking and turn it over to Dr. Reed, I'll post the link in here. But if you go to the HDIAC website, which is hdiac.dtic.mil/webinars, you'll see the webinar there, and the slide presentation is linked towards the bottom of the page. But without further ado, I would like to introduce Dr. Jeffrey Reed from the Naval Research Lab. And Dr. Reed, I will turn it over to you at this time.
All right, thanks. So the background for this is we reached out when we saw a information call from HDAC about what's going on in terms of the field of dust research, dust prediction, how are things changing seasonally, how are things going to change potentially in the long term. And like a lot of times that we deal with new customers, we had to take a step back and explain sort of the nature of numerical weather prediction, or in this particular case, numerical aerosol prediction. So we often not just work with you folks, but also with industry. And we here at the Naval Research Laboratory, we develop the weather systems that the Navy and other parts of the Department of Defense use. And sometimes it's good just to take a step back and get some perspective about how, you get your weather forecast in the morning. So, you wake up in the morning, the first thing you will do is like, oh, is it going to rain today? The same thing also goes for aerosol prediction. Like, I've got operations in the Persian Gulf. Am I going to run into a visibility problem for my carrier task group? Or is the temperature at some point also going to be too high for my guys to be really working in the field optimally, and things of that nature? So my colleague at NRLDC, Julie Rubin, and I kind of put this slide deck together. And again, this is very similar to, I do actually short courses sometimes for commercial entities. But the most important thing I want to point out from the very beginning is that this is a part of a community that, there are numerous weather centers around the world that do weather prediction, and they also a lot of them do composition prediction, not just for aerosol particles, but ozone and NO2 and things of that nature. And we collectively form a group called ICAP, International Cooperative for Aerosol Prediction. We all get along around the world, and we're trying to help each other out with data, in situ data, satellite data, model data. And if you take a look at that website there that we have on the front, we get together every year, and you can actually see, what are the sorts of things that we talk about in order to improve things like dust prediction around the world. So let's see, let me go to that. So, what's the bottom line up front? One of the things that I had a hard time coming to grips with when I started working for the Navy is, again, how big this field is. So I love this quote from Douglas Adams from Hitchhiker's Guide to the Galaxy. Space is big, really big. You won't believe how vastly, hugely mind-boggling it is. I mean, you may think it's a long way down to the chemist, but that's just peanuts compared to space. And that's really the way things are going in terms of environmental information, or all information, right? You can sit down and Google whatever it is that you want, and within a half a second you've got some answers. And that's because there are Costco-sized information centers running all over the country. The exact same things happen for meteorology and aerosol prediction. So one of the first things that you're going to have to come to grips with if you have an aerosol prediction problem, whether it's dust storms or chem bio, is that the field is by nature diverse. And that's because everybody has a slightly different spin on what they want and how they need to go about it. Some of these are resource limitations. Some of these like, hey, I just need this very, very simple answer, and this is the fastest way to get to it. But at the end of the day, when you talk about the aerosol prediction field, you just got to come to grips with that. It's this mosh pit of lots of people around the world that all somehow managed to kind of jump up and down to the same beat. The stuff that we're going to talk about today is that the data is classified into sort of three categories: in situ measurements, satellite measurements, and models. And then people pull these together, either through data assimilation or other forms of synthesis. And the other thing I'm going to sort of talk about is that times are changing. Like just in the last few years, aerosol related machine learning and artificial intelligence is huge. Commercial developers are a big part of that. And now we're going from kind of a government provided data to subscription-based sorts of business models. And so during all of this change, the folks that are successful in our business are ones that kind of keep their head together. They think about, okay, again, what is it that I need to do? Sequester uncertainty, and really pay attention to error and uncertainty. So for today's seminars, we got a bunch of goals. One of them, I just want to give some context to like what we care about in the Department of Defense. And even then, this is my perspective. I'm actually by nature an experimentalist. So I do a lot of verification work. I worry about like, what's the visibility going to be off of an individual ship? How well can we actually predict that? What sorts of post-processing can we do in order to get a better prediction? So I'll give some DoD context, but again, mileage might vary. I'm also going to then talk about the nature of battle space prediction and the streams of data that we have. I'll go over some community best practices, and then I'm kind of going to close with some thoughts on how things are changing in regard to machine learning, AI, and where industry fits into all of this. And then lastly, again, caveat emptor, no matter where you get your data, always buyer beware. Okay. So first, a little sales pitch for the Naval Research Laboratory. I'm here in the Marine Meteorology Division in beautiful Monterey, California. And the reason why we're here is because Fleet Numerical Meteorological and Oceanographic Center is here, and they do the forecasting of the weather for the U.S. Navy. Our division kind of has three major thrusts. One is we do basic research to sample, understand, and simulate the atmosphere. And in particular, we focus on coupled problems. How does the ocean interact with the atmosphere? How does the atmosphere interact with the land? How does the land interact with the atmosphere? And and so on and so forth. The cryosphere. And now, again, the laboratory as a whole is worrying more and more about space weather in the middle atmosphere. So we take all of this basic research and we develop tools and systems for that. And then these tools and systems are then applied to Navy problems, or in some cases commercial problems, so that we can make a better prediction, or basically make life better for the warfighter. And so the Naval Research Laboratory has a wonderful vertically integrated nature. And to be honest, this is what keeps me at the NRL and led me to come here in the first place, is that this is one of the very few laboratories in the United States, if not the world, where I can work on a basic research problem, do prototype development, and then actually work on and all the way in all of the applied science that's in between. And so basically here at NRL, we live in the valley of death. We really enjoy problems where we can take basic research, tie it all together and develop a system that we can hand over to a customer. And we do this for lots of sponsors throughout the Department of Defense, other agencies, and also industry. So, the sort of baseline example of why you want to do visibility planning, right, goes back to the Iranian hostage crisis, right? Operational Eagle Claw, where in like 1979, they actually sent in like Delta Force to try and extract the hostages in Iran. And it was just their bad luck that a monstrous dust storm happened right during their marshalling site, and things just went kind of downhill from there. In comparison, like 30 years later, Neptune Spear, the SEAL team that went in to go nab Osama bin Laden, they paid a lot of attention to every single detail. And the weather was just one of the many things that they really cared about when the SEAL team went in there. And, one of the aspects was, visibility might be bad and there's a chance of a dust storm. And they said that was just one of many, many things that factored into the exact hows and whens that they went after him. As a closer to home example, I mean, like we all live with this. Back in January here in Monterey, we had a giant lithium fire. So they have these giant battery plants now going all over the United States to help balance the loads for the power. For power infrastructure. And, it was very interesting driving home and seeing flames shooting 100 feet into the air as this battery plant burned for 3 days. But they said, don't worry, the air is safe, even though you have all of this burning lithium. EPA came in and they ran their models. And they said that all the smoke is going into the middle troposphere, and so you really don't have to worry about it anywhere near the plant. And then the next morning, we all found ash sitting on our driveways on our cars, and now they're finding heavy metals all around the area. And there are 3 legal firms that are canvassing the area, trying to get people to sign up to their particular class action suit to find somebody to sue. Right. So I'm not going to go into the details here of what they did right and what they did wrong, but it is something that affects us from the highest national levels down to what could possibly happen in your own backyard. So, from a Navy's point of view or DoD's point of view, these are the sorts of things that we have worried about in terms of aerosol applications. So it kind of starts off with safety of navigation, right? If, you launch a bunch of aircraft from your aircraft carrier and then the visibility drops to, 1 kilometer, 500 meters because a dust storm comes into the Persian Gulf, which is not uncommon. All of your aircraft have to divert to Bahrain, which is just a colossal pain in the head for everybody. At the same time, when I started working for the Navy back in the late 90s, it was all about see and be seen and how do you come up with tactical decision aids for sensors and target acquisitions. Also around that same time, in around 2000, 2001, there were lots of questions on Gulf War illness, and was Gulf War illness in part due to the fact that, we blew up all these chemical munitions and that air blew somewhere. Currently, directed energy sees a lot of investment, and it's very difficult to blow something up if you can't see your hand in front of your face. At the same time, you have things like obscurance, not just to protect you, but also to keep you being seen from a host of different weapon systems. But again, like directed energy, right? So if you want to defeat a directed energy system, the surest way is to put a cloud between you and whatever the laser is trying to hit. And then finally, there's ISR sorts of applications, like what can we do in terms of clever optics in order to see through clouds and haze in order to get a clear picture of what's going on at the ground. So, how do I think about all of this information? Actually comes from Rear Admiral Titley. He retired years ago. Now I think he's at Penn State. But he showed this slide, I don't know, 20 years ago. And it really resonated with me. So I use it all the time in these kinds of talks. And you have this sort of information pyramid. You could also call it the information funnel if you want to flip it around. But it really all starts on, what's your initial boundary conditions? And you've got observations from all sorts of places, whether it's from the fleet, or whether or not you've got even satellite data, or you've got a weather station. And then that goes into the tier one sorts of systems. And these are kind of the forecast systems. So weather models are what they call sort of the environmental layer. Also, if you want to do analyses, and we'll talk about what goes into an environmental model or meteorology or aerosol model. But, based on these models, then you come up with tier two, which is sort of the performance layer, right? So the performance layer is how do you synthesize all of this environmental data into how something is going to perform, whether it's a lock-on range for your IR system, or whether or not you're going to be able to recover your aircraft. And a lot of times with the performance layer too is that you will have probabilistic systems. There's not just one answer, but we'll give you an envelope. Like, yeah, you're probably okay tomorrow, but there's a chance that you're not going to be able to see the target that you're looking for. And then the hardest one is actually the tier three system. So this is the decision layer, right? Where, you take the performance layer and you really try and synthesize all the information for somebody who has to make a decision. And where that gets to be tricky again is quantifying risk, asset allocation, sorts of problems. And decision makers really don't like probabilistic solutions. They want to know, like, am I going to be able to recover my aircraft tomorrow? Yes or no? And the answer is when you say, yeah, probably, right? They don't get really happy. So let me give you an example of how something like this works. What's your particular problem? Right? Is visibility going to be good enough for me to go into port? Right? So if the visibility is less than a kilometer or so, you're not going to want to bring you don't want to bring your ship in to resupply. And what's the consequence of a bad decision? Well, I was planning on going into port tomorrow, and now I can't. And now I have all these people sitting on the dock waiting for me, and they're just kind of sitting on their hands. So how do I know whether or not it's going to be good? Well, we come up with the best estimate of surface visibility, and we also the probabilities of reaching some threshold. Where does that best estimate come from? Well, it comes from model, the Navy Aerosol Analysis and Prediction System, and for dust, the Coupled Ocean Atmosphere Mesoscale Prediction System. And, we can look at domains around the Persian Gulf and say, hey, this is what's going on in Bahrain versus what's going on in the UAE. And then where does that come from? Well, the models are driven by meteorology. And also we can use things like observations of dust storms through data assimilation to let us know where dust is being generated. And then we can essentially push that around with the winds on where it's going to be tomorrow or the next day and so on and so forth. So ultimately, this battle space and demand is really how the community works, right? So for boundary conditions in tier one, you've got obs and forecasts, and there's lots and lots and lots of resources for that. So some of them are agencies, NOAA, NASA, the Navy collects its own observations. We use observations from all around the world. Sometimes we even use them from universities. And then that feeds into the performance layer. So, for example, the National Weather Service will list a hazard for, say, fire activity. Like, hey, the fire weather danger is really high tomorrow. We need to worry about that. Or the performance layer for the Joint Typhoon Warning Center is like, hey, in 5 days, there might be, a hurricane, or a typhoon working your way into Yokosuka. Or for aviation, volcanic plume ash advisory centers are all over the world too, saying, hey, don't fly your airplane here. And then finally, you have sort of tier two and tier three, which are sort of really custom decision aids. And here in the Navy and at the Air Force, we have custom decision aids for SEAL teams versus what you're going to want to have for an aircraft carrier, or for plume dispersion. You can go to the folks at Lawrence Livermore. But more and more tier two, tier three, and actually even now tier one industry is becoming more involved. So way back when, right, there was AccuWeather, and then IBM bought out Weather Underground and the Weather Channel, and then a lot of people use Windy. for sort of sensible weather. But then, the power industry is very big on all of this data. How, is there going to be enough sunlight to drive my solar panels, or is there going to be enough wind in the area that I need? And, the energy community is always balancing the load in the energy infrastructure. Routing is huge. Like, if you take a look at where airplanes are flying on Flight Radar 24, they will route aircraft to avoid headwinds because, jets burn a lot of fuel. And like a really good example of this, of tier 1, tier 2, tier 3 all rolled up into one, is SOFAR. So you can buy yourself a SOFAR buoy for, I guess they can run about $3,000. You can deploy it. It has an Iridium phone to broadcast the data. So SOFAR takes the data, and then they also use that data in their own models to help with ship routing, right? So there's this sort of integrated stream of data from all the way from observations all the way up to your custom decision aid. So to get a handle on scale, this is an example of the Navy's framework, right? And you start off with observations, and when we join it with models, data assimilation. And I love the quote from Yogi Berra. It's amazing what you can see by just looking. So in order for us to run the models, we kind of need to know what the initial state is. And data assimilation is really is an error-weighted mean at the most simplified level between all of our observations, whether they're ground or satellite, and what you have in the model. So what's going on in the model? Well, at the global scale, here at Fleet Numerical and developed here at NRL is NavGem, and soon it's going to be replaced by the next generation model, which is Neptune. Seasonal models, aerosol models, and we all run these models at the global scale, and they deal with weather, they deal with ice and air-sea coupling and such. And depending on the product, you've got coverage anywhere from 1 degree to like 10 to 20 kilometers. Fleet Numerical runs a 5-day weather model and aerosol prediction every 6 hours for sort of medium rain guidance. Then there's the 10-day ensemble, there's seasonal forecasting, and then there's also the reanalysis, where we just go back and combine all of the model and satellite and observational data that we can, and to come up with the very best analysis after all the observations come in. And the way that these models work, it's literally a fluids model. Like, you've got the Navier-Stokes equation, and you've got your forces, and you're pushing these things together. And then with that stuff that's below your grid scale, then you kind of come up with parameterizations. And then you can go down to even finer scale. So COAMPS, coupled ocean atmosphere mesoscale prediction system, and soon there's a regional version of Neptune. Same idea, weather, ice, aerosol, but now instead of dealing with like 10 to 20 kilometers, you can actually run at 1 kilometer level and deal with things like orography. It's also a fluids model, just like the global model is, but it's got more complete physics, and because of its high resolution, it can take into account more fine features. Again, like depending whether you've got sea surface temperature fronts, or as I mentioned, orography and things of that nature. It's used operationally, but it's also used to support science and exercises. And it's also run at the center. But, they actually can run these things remote. So if you can send the boundary conditions, they've even running like mesoscale models in the back of a Marine Corps Jeep. And then you fuse all of this stuff together in terms of decision aids, right? So all of these NWP products, satellite and observations feed into all sorts of products. Again, like here, Buck Sampson and his team developed the automated tropical cyclone forecasting system, and really they want to know: am I going to get hit with a hurricane or a typhoon? Are the seas going to be bad? What's going on in terms of winds on site? We have systems like the Joint METOC Data Viewer and the ladder for doing ship routing. At NRLDC, they have the Builder program that does radar propagation. There's lots and lots of electro-optical decision aids about seen to be seen, power and bucket for directed energy, and of course there's plume dispersion. And that's just NRL, right? And the stuff that we deal with, and that's just the tip of the iceberg, right? In order for us to do what we do, people all over the world have to do what they do, right? So there's observations from airfields, ships. They report on visibility, sensible weather, whether or not there's fog. Lots of countries, but not all, but most countries publish near real-time data feeds that goes through the WMO. There's even personal federated networks now. Again, like if you go and buy yourself a weather station, there's a good chance that that data is, it is connected to the internet. That data is going to IBM. And then you can go to Weather Underground, and they do custom weather forecasts based on a lot of weather stations that are just, that's your neighbor's host. Or for air quality, there's Purple Air. And then also with all these different sites, there's lots of calibration and validation and long-term monitoring that we have to deal with. For remote sensing, again, there's all sorts of remote sensing data around the world. Obviously, there's the US, there's NASA, NOAA, for land surface, USDA, in Europe, ESA, EUMETSAT, Asia. And yeah, we even get our hands on Chinese satellite data. And for some applications, it's really quite good. For global modeling, for aerosol prediction, there's 9 centers that produce aerosol forecasts every day and make the data available to the public. And there's more that don't even make their data available to the public. So besides the Europeans, the Finns, the French, the Japanese, NASA has a run, NOAA has a run, UK Met Office has a run. And here at NRL, we collect some of the data from all of it and we put it all together, and we can see, like for a particular dust storm, are all the models agreeing that this dust storm is going to happen, or only a few of the models are thinking that a dust storm is going to happen. And then in terms of finer mesoscale simulations, small domains, I really lost count on how many people do that. I mean, it's in the dozens. I don't even bother counting the people that do plume dispersion because there's so much diversity in that kind of work. And then in terms of field campaigns that try and pull all this stuff together, there's dozens per year where you'll have aircraft and ship where they combine that with satellite data. And again, we try and sweep up this data when we can in order to verify and improve the models. So in terms of numerical weather prediction observations, if you go way back, everybody thinks about the weather balloon. Or again, like airlines and aircraft, they have automated systems on them that provide you with, temperature, humidity, and winds, a lot of marine observations and observer reports. But, the vast majority of observations actually come from satellite. And I love this image that was done by Dan Tyndall here at NRL in the building next door that just says, okay, like over the course of one day, and this was last year, how many observations go into the model? And it's 4 million, 5 million observations a day from all sorts of different sources. And we do things like use feature track winds of clouds from geostationary satellites to get to get the winds, infrared for cloud top heights and temperature, and sounding for temperature and water vapor profiles, radar, occultation from GPS, and lots of constituents, anything from ozone to aerosol, NO2, things of that nature. So from an observational point of view, specifically for aerosol particles, there's lots of networks out there. So if you go to EPA website, here in the upper left, those are all the sites that are either doing filters or running near real-time measurements, and all that stuff is made in near real time. The NASA AeroNet program of sun photometers is a staple for anybody who does global research because they do a really, really good job of collecting, quality assuring, and publishing the data quickly and easy to wait. And you can get data all over the world. They even have an ocean program called MAN where people with research vessels are always collecting data, and they all synthesize that. Global Atmospheric Watch, this is run by the GMAO, and basically these are people who develop their own field sites and participate in it. Lots of third-party aggregators now, like people will go in and say, okay, I'm going to take air quality data from India and combine it with the EPA and combine it with China, and they publish their data. A good example of that is OpenAQ. LiDAR networks. LiDARs are really finicky instruments that require a lot of maintenance, but there is a large number of them out there, and people are trying to figure out the protocols to be able to, to share data between, say, Europe or the United States and Asia. Everybody does everything a little bit differently, and so it's a big effort to sort of synthesize and harmonize the data set. And then on top of that, in 1 year, like this, ad hoc field campaigns and networks and things like that. So it's a big deal to actually try and synthesize all of this data together. From remote sensing point of view, this is kind of just the busy board. there are lots and lots of satellites out there. And they all differ in their sampling, skill, and technique. There's ones that just basically look at the light that's reflected from the Earth, to people who do stereography and they add polarization. And which one you use really depends on the application, whether or not you want to use it for data assimilation or you're just looking for a pretty picture. And one of the questions that you got to ask yourself whenever you start digging into all these different satellite data sets is, what is your baseline? Like, what is it that you're really trying to improve against that what you have right now? And again, it is a big deal trying to manage all of these data feeds, right? So what you're looking at here is just ESA, NOAA, and NASA, and then and you met Simi and JAXA, but the Koreans are now involved, and India now has their own fleet. And again, all of this data is flying around. So the point here again is you got to get back and figure out, well, yes, I could use all of these satellites, but do I need to? So from operationally, yeah, like you can come up with an aerosol product from a satellite that we never anticipated actually needing or getting an aerosol product from. And that's great. And if you're doing basic research, that's great. But when you think about consistency and timeliness and how well it's characterized, a lot of these satellite products kind of collapse down to just a few that we use routinely for data assimilation and verification. Okay, now flavors of aerosol modeling, right? So now we have all these observations, we have the satellite data, and the first question is where do you get your meteorology? And there's various types of aerosol models, right? There's inline aerosol models where you basically treat aerosol particles that, like you would water vapor, it's built into the numerical weather prediction model, and every time step there's an advection, and you have microphysics that feeds back in within the model. There's offline models where you basically take a meteorology 4D cube, and then you use that to push your particles around and scavenge them or produce them as needed. And in some situations, you know, you can just type it in by hand. Like I've got a plume dispersion. I think the wind's coming from the north and it's running at 15 knots. And I think this is what the stability is. And I'm going to type that in and I'm going to get a solution. Right. And then you ask yourself, what kinds of scales? As I already mentioned, you know, global scales, which is what I tend to work the most on, but you can run these models over a limited domain to 1 kilometer resolution. You can run large eddy simulation at 10 to 100 meter resolution, or you can even do, you know, direct numerical simulation at the 1 meter level if you need it. And then there's also analytical solutions. And so from a meteorology point of view, it really, you know, there's this trade space. I can be really large in coarse resolution, or I can go finer and finer resolution. And then I have to reduce my domain. So I'm working on a project with the Navy and NASA where we're trying to run 20-meter grid size over 150 kilometer domain, right? So super high resolution, pretty large domain from a large eddy simulation point of view. And it's a lot of work to be able to balance things and get it to do it. But there's things that we can do at that level that you could never do in a mesoscale model or a global model in a million years. At the same time, it's just computationally impossible to run a large eddy simulation over the entire globe. And the next question again is like, you know, how do you want to deal with your aerosol particles? So, you know, again, back in the day when I was really young, it's a lot of parametric models. There would be the Gaussian plume model, where again, I would type in stability and wind speed and direction, and it'll come up with estimates of where the plume could be. Most models are what are called Eulerian models, where again, you sort of advect a concentration of particles within the model, just like again, when you do water vapor. But now that computational efficiency is increasing, as is the number of core hours available, you can actually track individual aerosol particles in sort of Lagrangian trajectories. So if you look at here on the right, this is a large eddy simulation of vertical velocity that was done by one of the postdocs here, John Park. And you can see that vertical velocity upward motion, which is red, is in these sort of long strips. And in blue, you have this sort of subsidence. So again, you get like rapid increase or elevation in aerosol particles, rapid altitude gain in aerosol particles, and they kind of slowly subside in the boundary layer. And so, again, depending on your problem, do you need to track individual particles to understand the plumbing, or do you just kind of need to know roughly how the plume is going to disperse? And then you can scale this up as small as large as you need to. And then, the other question you need to ask yourself too is like, do you need an analysis? Do you need to just know what hit me? Or do you really need a forecast? And then finally, like, how do you want to deal with uncertainty, right? So deterministic, I'm going to put all of my eggs into one basket and do a run, or am I going to do an ensemble and run the model a bunch of times, slightly different initial conditions, and see how variable, like where I think the plume is going to be. So what does it take to get an observation into numerical weather prediction? Well, this is the process of data assimilation. And again, at the simplest level, so data assimilation is an error-weighted mean between the model and your observations. So you kind of start on the upper left with observations, why. And typically we'll use what's called aerosol optical thickness, sort of an integrated optical measurement of how many aerosol particles are in the atmosphere. But you can also assimilate surface PM, LiDAR data, radiances, and we'll ingest the data by doing pre-processing, getting it all into the same sort of file. We worry about things like latency. We'll do the basic quality control. And then we'll do, the next step is what's called observation error covariance, where we really do the error characterization. We worry about the representativeness. And we also worry about, is the error spatially correlated? A lot of times in data assimilation, you assume that every observation is independent from every other observation, but we all know that's not true because your observation method, has built into it its own biases. So we try and take those error covariances out. Then at the same time, you've got your model forecast, and your model also has an error covariance. And you have data assimilation, which again, we basically do is an error-weighted mean. So what you'll hear is that, you'll hear words like innovation. Innovation is the difference between the model background and the observations, and then you'll have the corrections. And there's a whole bunch of different solvers, mathematical solvers to do this. So what that looks like is here, for example, we have satellite and AeroNet data in the upper left at one particular time step. And because there's also latency effects between the satellite data and AeroNet and when it actually works its way in. We come up with a prognostic error model. We come up with literally an error estimate for every single observation that we have. You've got a model forecast here of this particular case. You've got a smoke plume blowing over from Canada over the United States. We have a standard deviation. Julie Rubin runs the model 80 different times with slightly different initial conditions to see how sensitive the system is. And then up here in the upper right, we have a correction. So essentially combining the satellite data with the model, you can see where we're adding aerosol mass, in this case over New York. And then you go a little bit further south to Philadelphia, and we're reducing the aerosol mass. Essentially, when you see this dipole, we're shifting where the plume is. And then we get another analysis for aerosol optical thickness, and the whole process starts all over again. All right, so let's take a deep breath. Where do you start, right? And the most important thing is define your problem very, very clearly. Like, what is it that you really, really need to know? You need to know the position of a plume or the probability of where the plume could possibly be if you're talking about a toxic emission. Are you good with the climatology? Yeah, we're going to deploy Marines to this particular beach, and the probability of there being a dust storm is this. Or do you need to know where a dust plume is going to need to be in 2 days? Again, deposition and exposure sorts of problems. And then the next question is how well do you really need to know it? And then ask yourself the question, what if you're wrong? Right. And one of the scientists here that actually founded the aerosol program at NRL, Doug Westfall, had a great saying, which is, when is a bad answer better or worse than no answer? A lot of times, we don't know, and we kind of come up with an answer. Are you actually doing the customer a favor then or not? And again, you just said there's different levels qualitatively. Do I need to know what just hit me? Or do I really need to know whether or not I'm going to get hammered tomorrow with a dust storm or a smoke plume? to very, very quantitative questions. So lots of people in the scientific community are asking, do we need to include aerosol particles in the actual weather forecast themselves? Because the way that aerosol particles can interact with clouds or perturb the radiation field of the atmosphere. And so what's the difference between, you know, qualitative and quantitative? Well, the first thing you got to come to grips with that, even the big flagship projects, I should say, they have errors. And so we always are worrying about error estimate. It doesn't matter where it comes from. It can be supposedly the best, cleanest data on the planet, and we still worry about the error characterization of that data. Again, also the other problem is that lots of people are posting data now, and just because somebody posts data doesn't mean that it's right, or it's not right, or it might be right for their application, but it might not be right for your application. And probably the most important thing is that precision is not the same as accuracy. You will see now some really beautiful animations. That doesn't mean it's the right planet, but it is a beautiful animation. So you kind of got to ask yourself again where you are on that qualitative to quantitative spectrum. And then the other question you got to ask yourself is, what are the resource requirements? You know, do you know what it means to use that product? And can you even get to where you want to be based on the product that's available to you? And maybe you need to go back to the library. Do you have the time and capability or even hard disk space? We run into this all the time. Oh, I don't have the storage capability to do my problem. I was like, well, then you need to figure out what your resource requirements are. Upstream dependencies, right? Because there's all of these data sets that are out there, you have to worry about what happens if one of the little cogs doesn't turn that particular day. And that's, you know, any nerd loves XKCT comics. And this one works its way around NRL all the time. Again, like, you know, some project a random guy in Nebraska has been thanklessly maintaining since 2003, and then he decides to take a vacation one day, and all of your other infrastructure comes down. That does happen. And what does it mean if you have a forecast or a product doesn't arrive on time? So the other thing to think about is sort of concepts of different levels of, again, of what kind of data you really need. And I like the way that NASA defined all of this 30 years ago. Like, do you really need the root data, what we call level 0 data? Probably not. Do you need calibrated corrections, annotations, georeference data? That's kind of level 1. If you're doing a secondary calculation, you know, you've got the radiances, but I want to calculate, you know, okay, I just need to know qualitatively if a dust storm is there. That's a level 2 product. Do I need to have it gridded and averaged and put into a systematic time series? That's level 3. If you want it to be consistent with model data, that's level 4. Or you might even just be okay with an equation. For example, from a NASA, again, they have all these different archive centers that you should poke around with if you need the raw data, right? Level 1 and level 2, you go to the DAX. They have a wonderful Giovanni portal if you want to slice and dice aerosol data for your problem. And then if you want level 4 products, you know, the NASA Global Modeling and Assimilation Office has products like that at NASA. Or maybe if you need a pretty picture, you know, picture's worth 1,000 words, try out NASA Worldview, or the European version is UmetView. These are wonderful websites just to see what's going on in the particular neighborhood that you're interested in. Or if you're just interested in an equation or a synopsis, go to the library. Again, starting points for public data repositories: NASA, NOAA, ECMWF, UMetSat, Japanese. Again, I have all of these in here if you want to just poke around if you're interested. And then from the Navy archives, you know, if it's distribution statement A, we have the G'day server here. If you've got a CAT card, you know, use FinMock portal. And then we also have experimental visualization, and we're always looking for alpha and beta testers for this. So on the distro A, we have MapRoom :8443, or the distro D site. It's just MapRoom, and that's where, you know, that's kind of where we fuse products together, and we see, you know, we use this as kind of a test bench. Oh, does this product actually compare well to this other product? So if you want to compare various models, or you want to compare, does my satellite data look like my model data or my observations? MapRoom is a really good site for that. Again, it's a developmental site, but we're always looking for alpha and beta testers. And if you have other questions about Navy data, you know, feel free to drop me a line and my email there. All right, so the last thing I kind of wanted to finish up with is on AI and cloud computing. And, you know, and can AI help with all of these data issues that we have? And if you just go to Web of Science and, write aerosol and machine learning. This was actually, I think from last year, we had 1,100 results. And AI definitely has some advantages, right? So AI platforms are popping up like mushrooms, and they're really good at harvesting and communicating qualitative information. Even then, you got to trust but verify. And it's getting there for reformatting data. Like if I have aerosol data in such and such a format, and I say, hey, I want this in an Excel spreadsheet. Sometimes they can do that, not always. Or you can say, write for me some Python code that can convert this, this binary file into an ASCII file, and it'll get it about 80% of the way there. And you need to go in and fix it, but at least it'll get you started. Where AI has problems is on equations, physics, and abstractions. So if you say, give me the algebraic approximation for da 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 da, more likely than not, it's going to give you a wrong answers. Since I was in this business, which is 30 years, we've always been begging to get access to computational resources where data is housed. And that is now happening in the cloud, which is sort of good news. And, these AI and machine learning methods are exceptionally data heavy. So if I can go to Amazon or Azure or any of these other cloud platforms, and NASA puts the data there, and I need to go through a lot of this data, that's going to be great because I can just do my computational there. I don't have the egress charges, and I can whip through things quickly, which is really great. But with that, we got to ask ourselves a lot of hard questions. The most important of these, with all of the aerosol meteorology data, is the cost accounting for this model was very optimistic, I will say. And then you got to ask yourself about account management. Like before, you would get a research grant, and I bought a computer, and then I had that computer, and I could do with it whatever I wanted. Now you get a research grant, you get an allocation on whatever cloud services the sponsor is paying for, and now your research grant is over, and you can't even get at your own stuff unless you pay somebody. And so this is a growing pain that people are going to have to work with. For AI and machine learning, it's great for individual product base. I need just an estimate of surface visibility, right? But if you need to do physics where, well, I need to know why the visibility is bad, that becomes more of a problem. And my concern is that it's hard enough keeping track of the flagship products that come out of NASA and NOAA and the Europeans and the Japanese. Now there are hundreds of AI machine learning products that are half-baked, and being able to sort through them and doing verification is a problem. And again, I'm not saying this development is good or bad, but it is going to be different, and we really have to push for rigor. And that's a community thing. Like, people have to prove that their products actually do what they say that they do. Industry and observations. Again, it used to be NOAA that would maintain weather stations and that data feed. Now you're going to subscription services. Faisala has been doing that for years when it comes to lightning data. And now you're seeing other companies, whether it's buoy data or balloon data and things of that. And there are arguments against subscription services. And I can't politely name some of the bad hats in the industry, but there's also an argument on why you may want to do it, right? Competition is good, right? And I think that goes for government as well. But you got to play by the same ground rules. And sometimes, again, commercial can be really, really innovative and do things that like the laboratories can't be. They can be agile. And a lot of times too, we like to think we were in our ivory tower, and that we think physics, but we were as empirical as some of the companies are as well. And keep in mind, it's not a zero-sum game. Market capitalization is growing. If you can eke out a little bit more of a profit by using aerosol or weather data, people are going to do it. And just an example, you can go to, I saw this market investigation on Earth observations and where the money is. And you see a lot of this is going into defense, but it's also going from all sorts of different countries. And for $6,000, you can pay for a report on what's going on in terms of data. So then you got to ask yourself, right, is $6K really worth it. My concerns, and all of this is on a case-by-case basis, is a lot of people that are pushing data really don't know the nuances of the data, and then you run into quality assurance problems. There's black box issues. There's consistency because they also have turnover in the people that do work. I will say there are sometimes unfair business practices, and then if you give feedback to a company, that feedback to them, it becomes proprietary for them also. And you also worry about longevity of data products. You don't want to buy into a subscription service and then have that company go out of business in 5 years, and then you got to retool. Industry and prediction is kind of the same thing. There are lots of companies now that are doing weather prediction, not just IBM. Microsoft Aurora is in it. Energy traders have been really successful in this because lots of money's at stake for small changes in the environment. For things like air quality and aerosol, is there that much of a value proposition? Well, there's regulatory, but people generally don't pay to regulate themselves. And also keep in mind, this industry and prediction is all based on government furnished data streams, particularly model. Like a lot of these things, again, will train off of ECMWF or NOAA. And where they're good at is debiasing data. They're not there yet when it comes to prediction, but we debias as well. So again, there's issues on like, are they really doing what they say they're going to do? And they scorecard well because they train against the scorecard. But again, a lot of times you'll actually look at the meteorology and like, that just doesn't look physical. And again, it's good for isolated products, but if you need consistency across variables, it becomes a bit problematic. We certainly can't be dismissive, but almost certainly we also, again, need to be sort of buyer beware. And so then a final word on caveat emptor, right? Keep in mind, again, like what we're talking about here for meteorology is like space. And even the aerosol community is a big, big, big field. And so don't ever forget that everybody is bound by the same laws of economics, you know, even including altruism. So everybody's kind of pushing their own stuff, and then independent verification is important. And getting funding for independent evaluation is difficult. Keep in mind, again, more complex is not necessarily better. They can say that, you know, their product came from running on a supercomputer, but that doesn't mean that it'll do a good job. And our experience is that for the most part, model complexity does not directly correlate with skill. Just because a model is complicated does not mean that it's good. And just because something is simple doesn't mean it won't do the job for you. Definitely go to the library and search for verification publications, especially independent, right? People, again, are not gonna highlight where their own flaws are. And do your own sniff test. In the back of your mind, you're like, you know, this just isn't quite right. You should listen to that, right? And then go down the rabbit hole. And there's lots of different products out there, like Worldview. Like, oh, does Worldview show there's a dust storm wherever the model thinks that there's a dust storm? And certainly, again, reach out, talk to other users. Again, the reason why we've been as successful as we have been is that we work as a community. All right. So how do you feel? I know it's a lot to wrap your brain around. A few of us here actually do multi-day short courses on this kind of material. But keep in mind, I know some of you are probably aware of everything that's going on, but also some of you probably aren't aware of all of the things that's going on, and you can take advantage of this for your own purposes. Just again, keep in mind that the reason why there's diversity is because there has been opportunity, and these sorts of problems project on all sorts of things. But just to finish up again, here are a few pointers. Again, define your problem really, really well and gauge that against your error tolerances. I mean, it's easy to say, oh, I need an aerosol product for this, but really take some time to think about what it is that you need. Simple is good. And if you decide to go off the reservation, make sure you know what the rules are before you try and break them. Use the library. And again, like DTIC and HDAC, like throw in an advertisement for them. There are these resources out there. Don't try and figure some of this stuff out on your own cold, but there are resources you can reach out to, and they can get you started. You keep up, partner. I got friends all over the world, and we're always talking to each other because things are changing. And if you try and do stuff in isolation, you're going to get left behind very quickly. And again, I can't emphasize enough, verification, right? I know this isn't Missouri, but show me. Feel free to contact me if you got special questions, if you're looking for a particular data product. I certainly don't know everything, but I know a lot that's going on, and I might be able to direct you in some places for ready-made products if you might need, or if you've got specific questions. And at the end of the slide, I got just a bit, but at the end of the slide deck, just a bibliography of some of the stuff that I've worked on. Again, there are thousands and thousands and thousands of papers on these things, but these are stuff that people are getting used to the business. Should probably at least glance at the abstract and some of the figures to understand how things are going. And with that, I'll be happy to take any questions.
Well, thank you so much, Dr. Reed. That was an absolute tour de force, and it sounds like you turned a several day short course into a 1 hour webinar. Did it quite well, but yeah, that was I appreciate the image up front of the dog drinking from the fire hydrant. We'll have time for a couple questions, and if we don't get to your question, I will have like a kind of printout of the chat, and I should be able to maybe pass them on to Dr. Reed and get an answer to the question if it warrants it. So, first question that I picked up, depending on atmospheric conditions, Los Angeles could be downstream phi curl, which I'm sorry, I don't know what that actually is, but from Monterey County. Are we utilizing aerosol stream data to monitor this level of application?
Yes, absolutely. And we could even do in later time, we can do online demonstrations. So depending on the nature of the problem, you have different agencies that deal with it. So, in the Navy, again, we focus globally because the Navy operates anywhere. And then we'll also set up domains for the Persian Gulf or Asia. I think right now I think they're running like close to 80 mesoscale domains over at Fleet Numerical. But within California, there's folks associated with the Air Resources Board or the individual air quality districts that run air quality models. So, like, for example, going way, way back is CMAC. And they will take, they will have emission source functions, and then they'll take the meteorology and they'll deal with the chemistry, and they'll say, okay, like one of the big problems in LA is the Central Valley. Or actually, I should say it's the other way around. A lot of times pollution from LA works its way into the Central Valley, and that crosses jurisdictions. And so those air quality districts are looking at observations and models to see whose pollution is blowing into someone else's domain.
Wonderful. Great answer. Thank you so much. Another question simply is, are the 1 kilometer runs available?
Yes, and again, the question is it depends where. The global data streams are easier to archive, but depending on the domain and who's providing it, there are, again, lots and lots of data repositories. So if you go to US GODAY, they do some of at least for the meteorology, they archive some of the COAMP simulations for, say, the West Coast of the United States or the East Coast of the United States or Florida. But it really depends on what area you're in. But there are so many mesoscale model runs that are done there by different folks. You need to hunt around, and almost all of them now will have an archive somewhere. For the United States in particular, at the mesoscale, like the 1 kilometer, there's NOAA has a simulation called the HER, and they have a repository for that, and that I think is running at 1 to 2 kilometers, and that's for the contiguous United States.
Okay. Another question. Your large scale eddy model, can you run that degree of fidelity over a larger scale on a larger system such as Oak Ridges?
Okay, so the answer is yes, if you have the computational power to do it. So, the trick with large eddy simulations is that you're running high resolution, so you need lots and lots of computational power. Like if you start increasing your domain size, that goes by the domain cubed. So I'm working on a project right now with the folks at the Jet Propulsion Laboratory in Notre Dame, where we're running 150 kilometers on a side at 30-meter resolution for 7 days straight. And there are other folks who do that kind of work. It is an unbelievable amount of data, and they don't always sit in an archive, but it definitely can be done if you've got the core hours to do it.
How fascinating. So, probably the last question we'll have time to get to, but how do you use these atmospheric models in radiological analysis to calculate ground dose maps?
Okay, so technically speaking, NRL doesn't. So if you're saying how do we, because again, like that one is not part of our clientage, but you absolutely can do this. And to give you an example of this was Fukushima, right? So when there was the power plant after the earthquakes, and then you had the tidal wave, the tsunami that came in and basically took out the cooling system, and then Fukushima emitted. There were lots of different groups that tracked ocean, but also atmosphere. So again, you have an emission, the wind basically blows it around, and the particles either settle out, or most of the time the particles are actually precipitated out. So we actually look at as I said, everything in terms of the life cycle. And I guarantee you that there are numerous papers, if you go to the library, on dosage estimates for things like Fukushima.
Wow, great. Thank you so much. Dr. Reed, thank you for a wonderful presentation. I will remind all the attendees that this presentation has been recorded, so it should be up on our YouTube channel in probably the next 24 to 48 hours. I put the link to our YouTube channel in the chat, and then you can go to the webinar announcement page to download the slide presentation, which has Dr. Reed's email address in it. And also the YouTube link will be posted there once it's up. And if you need to reach Dr. Reed, I know he left his email address there, but you can also reach out to HDIAC, and we'd be happy to link you up. But again, Dr. Reed, thank you so much for this amazing presentation.
Anytime.
All right. Thank you.